Hello there. This video is for 3.6. I'll be covering two main objectives. First is just to go over the new derivative shortcut rule about differentiating logarithm, both the natural logarithm and a logarithm with any base b. And then the second objective is to show you a technique that is usually referred to as logarithmic differentiation. And I'll explain a little bit about what that is and why that's poorly named, and maybe give you an alternative way of thinking about that technique. All right, so the first thing is the derivative shortcut rules. We have derivative shortcut rules for virtually all the functions that you learned prior to calculus, aka pre-calculus. Logarithms were the function that was defined as the inverse of exponential functions, and we have shortcut rules for logarithms. You can see them either on your reference sheet or here again. I've cut and pasted them here. The derivative of the log with base e, called ln x, is just 1 over x. And if you choose a different base b, then you have to multiply by a factor of 1 over the natural log of b, kind of analogous to the derivative of e to the x versus the derivative of b to the x. Very, very similar. All right, we're going to do a couple of example problems. They're not that much more interesting than all the other derivative problems that you've done before and that I've demonstrated here. But before I do a couple of demo problems, I just want to show you an example of the power of the chain rule. We do know how to differentiate many things, but you have to sort of take my word for it for the derivative of ln x unless you want to see how it's derived. And the derivation is extremely simple, and it uses implicit differentiation. It uses the chain rule. So I'm going to start with my function, y equals ln x. And again, I don't know really how to differentiate ln x without just using this chart. So I'm going to simplify this by basically using the fact that it's the inverse of the exponential. So I'm going to raise both sides with a base of e. E to the ln x is simplified just to be x. And over here, e to the y, I don't know how to simplify it. I'll write that as e to the y. But the thing about this is I know how to differentiate both sides. I know how to differentiate e to the y, and I know how to differentiate x. So I'm going to apply the derivative ddx to both sides. This may start to look familiar with how we do implicit differentiation. The derivative e to the y is e to the y times the derivative of y. And the derivative of x is 1 times the derivative of x, which you may now know is 1. And this is the thing I want to solve for, dy dx. And so to solve for dy dx, I'm just going to divide both sides by e to the y. Here, the e to the y and e to the y divide out to equal 1. Here, I don't really have any simplification. I have 1 times 1 on the top, and I have e to the y on the bottom. So what happens here is I have dy dx is equal to 1 on the top and e to the y on the bottom. And that is the derivative dy dx. It's 1 over e to the y. We can simplify this very simply, though, because remember, over here, I'll do it maybe in green, e to the y is simply identical to x. We started off with y equals ln x, and I simplified that using e as a base, and that turned into e to the y equals x. So this e to the y is identically equal to x. So instead of writing this as dy dx over equals 1 over e to the y, I can write this as dy dx equals 1 over the thing that I can say is equivalent to e to the y, which is x. Remember over here, e to the y is the same as just x. So this is the formula dy dx is equal to 1 over x. So just by using the chain rule, we can simplify this function and find its derivative. In fact, any kind of inverse function is easily differentiated using implicit differentiation using the chain rule. All right, so that was a little demo of the derivative formula for natural log x, for the shortcut formula for natural log x. All right, I'll do a couple of examples here. Example A, I have y equals cosine ln x. So we have our traditional inside function here, and we have cosine as our outside function. So I'm differentiating cosine of thing. And so I'm going to differentiate both sides. I'll take the derivative on the left-hand side. I'll take the derivative on the right-hand side. I'll just make a big parenthesis to say I'm doing it both sides. The derivative left side is just 1 times dy dx. And the derivative of the right side is, the derivative of the cosine is negative sine. So it's negative sine of thing times the derivative of that thing. But since we know how to differentiate Lx now, then we get dy dx is equal to negative sine of ln x times 1 over x. And I guess we could combine the ones together. There's a 1 in front of the sign, a negative 1 in front of the sign. So we can write this as negative sine ln x. And we can even put the x on the bottom, just combine those two fractions together. So I guess that's a simplified version of dy dx. Negative sine ln x, all divided by x. All right, one more quick example here. I have log base 2 of some stuff of x squared plus ln x. So once again, I'm going to be using our new formula for the derivative of log of any base. It's 1 over x times that factor of 1 over natural log of b. So I'll differentiate both sides. So I get the derivative of y with respect to x. If I differentiate both sides, then the left side is just dy dx. The right side, the differential of a log is 1 over the argument, 1 over stuff in this case, times 1 over natural log of the base, times, don't forget this, the derivative of that inside function. It's not ln x or log base 2 of x we're differentiating, it's log base 2 of thing. So I have to multiply by the derivative of this thing at the end. So make sure to keep that organized. The time symbol. So dy dx, honestly, I'll write the number in front, and then I'll write the 1 over x squared plus ln x fraction next. And then to differentiate this thing, I have a derivative of x squared, which is 2x times dx, which is completely unnecessary since you all know that that's just going to disappear. And then I'm going to be adding in the derivative ln x, and the derivative ln x is 1 over x times the derivative of its variable. And once again, I'm just wasting time by writing dx. As you know, as I've said in previous videos, I'm writing this to help people understand what's going on. I don't expect you to write dx in your assignments unless you want to, unless it's helpful, then please go ahead and do that. But I do want people to understand what's happening and not just wonder when you put things and when you don't put things. I don't want it to be random. I want it to be purposeful. All right, let me just clean stuff up a little bit. Dy dx is equal to this number here, this fraction, and then we have a parenthesis at the end, which is 2x plus 1 over x. And I'm not sure if this really can be simplified much. It doesn't appear to be things that can be combined together very much. So I'm just going to leave it as that. Notice I have to put 2x plus 1 over x in parentheses, otherwise it is incorrect. It is that entire thing that is the derivative of the inside function, the chain. All right, so there's a couple of examples of doing our normal derivative rules, but incorporating another shortcut formula. As we learn more shortcut formulas, you just incorporate them into the same kind of derivative problems you had before. They just get more complicated and longer using different formulas, etc. Let me switch to the second objective, which is logarithmic differentiation. Explain how that works. All right, so just a very brief primer on the rules of logs. To simplify logs, we have several rules, but we have 3 very, very common rules. These right here, if you need a review on logarithms, you can let me know. You can look up the Canvas review sheet, or you just practice things online if you'd like. But these rules are very oftentimes used to simplify logarithms. When your argument has an exponent on it, when you have 2 things multiplied inside your argument, or 2 things divided inside your argument, we can simplify them quite nicely. We're going to exploit this in the method called logarithmic differentiation. All right. So first of all, let me tell you about what this might better be described as. We are definitely dealing with the derivatives of logs. I mean, we learned how to differentiate logs according to that shortcut formula in the last couple of problems we did. But really what I want you to understand is this is more akin to logarithmic simplification. What we're just doing is we're using the logs to simplify the function before we differentiate it. So we're not really doing any derivatives with the logs. We're using logs in a very strategic way to simplify before we do a derivative. So let me show you that a little bit more. It'll make more sense when I show you a couple of examples of this. All right, so my first example, labeled A over here, I have x to the fourth plus 5, this thing raised to the sixth power. It's being multiplied by sine x being raised to the seventh power, and it's being multiplied again by x cubed minus x to the second power. I guess you could try to FOIL out x cubed minus x squared, but this is going to be just a nightmare to try to simplify. And I think the easiest way would just to be like do like a triple product rule. Do the product rule the first two, and then whatever you got there, do the product rule with the last one, and you get all kinds of different product rules and chain rules and all kinds of stuff. Not fun, very, very long problem. However, these problems are exponent problems. They're things raised to a power, and they're multiplication problems. The things are multiplied together. And remember, logs are very, very good at simplifying when things are multiplied by each other and when things are raised to an exponent. This is precisely what logs are very good at simplifying. Now, there's no log in this problem, but that doesn't matter. We can just introduce a log, So what I'm going to do, the strategy here is to take the log of both sides. So I'm going to take the log of the left-hand side. I'm going to take the log of the right-hand side. The equations are the same now. I mean, the left side and the right side are still the same because I've done the same operation to both sides. But I can now simplify this using my log properties. So these things are multiplied by each other. And anytime you have two arguments, two things in the argument multiplied by each other, I can write them as two separate logs that are being added together. So left-hand side is ln y. This would be ln of this first critter plus ln of the second one plus ln of the last one. So I've now converted basically a product rule problem into a sum rule problem, which is way, way easier because I can just differentiate them separately. I don't have to necessarily worry about the product rule anymore because there's no products. I could do even better than that because each of these log things have an exponent. There's an exponent of 6. There's an exponent of 7, 6, 7, and here's another exponent. And once again, logs are very, very good at simplifying exponents. And in fact, the argument raised to an exponent, the exponent just becomes a coefficient out in front. So I get ln of y. This 6 is going to come down in front. 6 times ln of x to the fourth plus 5. And then I'll bring the 7 down. And lastly, I will use the formula to simplify, making the square into a coefficient of 2 in front of the logarithm. So without doing this, we'd have to use some sort of chain rule thing with multiple chains and multiple exponents. But now we've converted those exponents into just numbers multiplied. And the constant multiple of a function, the constant doesn't really change anything. It just kind of gets carried along in the derivative shortcut rules. So when I differentiate this, the 6 is just going to hang out. I don't have to worry about using the product rule or differentiating that. It's just a constant, so it just gets brought down. So I've tried to demonstrate here how taking the log of both sides allowed me to simplify this very dramatically before I take the derivative. I'm going to be taking a normal derivative just like we did before. Nothing special about that, but I use logarithms to simplify before taking the derivative. So just to recap, when is this logarithmic differentiation or logarithmic simplification helpful? It's helpful specifically when you have things raised to a power, things multiplied by each other, and things divided by each other. Anytime you have a combination of those things, logs work great to simplify them. If you have things added together, log's not going to help you because there's no log simplification formula for two things added together. You have to have them multiplied or divided or raised to an exponent. All right, so that's when this logarithmic differentiation technique is something you might consider using. And I made these problems sufficiently complicated so that you'd be motivated to see the usefulness of this technique. All right, so we're going to differentiate both sides. I'm going to differentiate the left-hand side with respect to x. I'm going to differentiate the right-hand side with respect to x. And I'll be doing my normal, chain rule differentiation, implicit differentiation, etc. The derivative of ln y is 1 over y times the derivative of y. The derivative of 6 times this thing is 6 times the derivative of ln of x to the 4th plus 5 is 1 over x to the 4th plus 5 times the derivative of x to the 4th plus 5, which is 4x cubed times dx dx plus 0. The derivative of 7 ln x would be 7, 1 over sine x times the derivative of sine x, which is cosine x, and dx dx. And then lastly, I have this 2 times this ln thing. So the derivative ln of stuff is 1 over stuff times the derivative of stuff. The derivative of x cubed would be 3x squared dx dx. And the derivative of minus x is just minus dx dx. We'll squish it on the side here. Okay, and of course I don't have to write all the dx dx's. I'm just doing it because I'm silly. I have run out of room, so I will just sort of make this separate. And 1 over y dy dx equals, I'll just put this as one fraction. And this right here, 4x cubed times dy times dx dx plus 0. This dx dx, of course, is 1, which I would imagine not many people would write in that situation. Just trying to expose what's going on here. So I have 6 times 1 times 4x cubed. So on the top, I have 24x cubed. And on the bottom, I have x to the 4th plus 5. The second fraction, I have a 7, a 1, and a cosine x on top. So we'll call that 7 cosine x over sine x. If you wish, you could write this as cotangent if you remember those trig simplification formulas. The dx of course, isn't there anymore because it's just multiplied by 1. And lastly, I have this 2 times this critter right there is 3x squared minus 1, and the denominator is x cubed minus x. I guess I could multiply the 2 to both of these guys, distribute if I wanted to, and get 6x squared minus 2. Maybe some people would like to do that because there's a number here that can be clearly combined with the other numbers. I think that's probably a good idea. Okay, we are not quite done because remember, our goal is to find dy dx. And we don't have dy dx isolated. So just like in our previous practice on implicit differentiation, whatever you do to both sides, do derivatives, you do need to stop only when you have solved for dy dx. And we almost got it, actually. We just have a 1 over y. And to get rid of 1 over y, that's a division problem. The opposite of division is multiplication. So I'm going to multiply the left-hand side by y, and I'm going to multiply the right-hand side by y. I'm not going to distribute, and I'll show you why in a second. Y times 1 over y is just 1. So I get dy dx is equal to y times this mess, which I will write down right here. La, 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 la. Okay, almost done. And we said we're going to write this as 6x squared minus 2 by distributing the 2 to this fraction thing, and x cubed minus x. All right, so I do have dy dx by itself. So presumably we are done. We found the derivative. We solved for dy dx. Everything is good, hunky-dory. However, we are going to ask you to simplify this one more step. And it's kind of like what I showed you in the demonstration of why we know the derivative shortcut formula for ln x is 1 over x. I use the fact that I can substitute in the end for what y is. And for these problems, we could do the same thing. If you go all the way back to the beginning, we are told what y is. Y is simply x to the fourth plus 5 to the sixth times sine x to the seventh times x cubed minus x to the second. I mean, we know what y is. So it is considered very good manners in calculus to write out your answer all in terms of x. So that means dy dx. Come on, pen. Dy dx is going to equal, well, y is x to the fourth plus 5 to the sixth times sine x to the seventh times x cubed minus x squared times, that was just y. That was the y thing. And then I have this big parentheses, which I'm not even going to have room for. And the big parentheses, let's see if I can make more space over here. Okay. Is all this stuff right here. This is my big parentheses that I'll have to write afterwards. So the y has been substituted in as the original function. And then I just write this rest of the stuff, which will take me some time because my pen is kind of goofy right now. All right. Of course, you can skip if you don't want to watch me writing down each thing, but it's just, I'm just writing down the stuff in the parentheses to finish the last step of this logarithmic differentiation problem. And it's not necessary to multiply this all out. You don't really get anything by doing it. So we're just going to leave our answer like this. Okay. Boom. That is my derivative answer. Let me just zoom out a little bit for this first example in using logarithms to simplify before doing a derivative. So my original function was this crazy thing up here. And I used logs to simplify it, differentiated using implicit differentiation. And importantly, I substituted back for y at the end. You will lose a point or two on a test, or of course, WebAssign will mark it wrong if you don't convert it back into the y. So kind of remember that last step. Okay, I got one more example for you before the end of the video. This last example here, I'll just write again because, you know, I didn't do very good space management. So I'll just write down example B right here. It is the function y equals x over x squared plus 1. Come on, pen, you can do it. And that entire thing is raised to the fourth and being multiplied by 2 to the sine x. So this is the time in the video where I implore you to pause and try this yourself. I will pause the video and write out the steps and then show you sort of the overview of my approach at finding the derivative of this example B. So if you have the energy, please go ahead and pause the video and give that a go. And then you can see if you get to the end or if you got stuck somewhere where you did get stuck, so I can get you unstuck, and then you can sort of make sure you can learn from that experience. All right, so we're going to find the pause button here. All right, so welcome back. I wrote out my solution, and hopefully you had a chance to try it too. So here's my approach. I have this function, and there's some division, some multiplication, some exponents, a great candidate for simplifying using logarithms. So I apply a logarithm to both sides, and that allows me to use the simplification formulas to simplify. I do have a product of two functions. I have this x over x squared plus 1 to the fourth times 2 to the sine x, so I can write them as two separate logs being added together. So basically converting a multiplication into an addition by writing it as two separate logs. Each of these logs has an exponent, so I wrote the exponent down in front, 4 in front of this first logarithm, and the exponent is sine x, so sine x was in front of the second logarithm. Focusing on the first logarithm for a moment, this is log of a fraction, two things being divided, so I can write them as two separate logs being subtracted. So I get log of the top minus log of the bottom. And those are all multiplied by 4. And then I still have my sine x times ln2 at the end. Now that I've simplified it using my log formulas, I'm going to differentiate both sides, differentiate the left, differentiate the right with respect to x. The derivative of ln y with respect to x is 1 over y times dy dx. Still have that 4. Constants by being multiplied don't affect derivatives. So the 4 is still out there. The derivative of ln x is 1 over x times dx dx. I just wrote it as 1 over x times 1. And then minus the derivative of ln of stuff is 1 over stuff times the derivative of stuff. So 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x times dx dx. And lastly, the derivative of sine x ln2. Ln2, if I remind you, is a constant, right? It's like, sine of 2 or square root 2, log of 2. Those are all just numbers, right? And so this is a number times a function. Again, numbers being multiplied don't affect derivatives, so I don't have to use any kind of product rule here. The derivative of sine x is cosine x times dx dx, or cosine x times 1, and then I just multiply by ln2 at the end. That's how we got this second part. All right, so that's 1 over y dy dx is equal to that entire thing. I'm going to multiply the 4 through just to combine things together. If I multiply the 4 through, I get 4 over x and 8x over x squared plus 1. And then I don't need to have those parentheses anymore. I can just say plus the cosine x ln2. I do need to solve for dy dx, so I'm going to multiply both sides by y. So this side's being multiplied by y to simplify this. And of course, I have to multiply the side by y, which is why there's a y here. And then the last step, remember to rewrite that y in terms of the original function. The original function, my friends, is up here, x over x squared plus 1 to the 4th times 2 to the sine x. So I dutifully wrote in the original function, x over x squared plus 1 to the 4th times 2 to the sine x, times this glop right here, that I differentiated the right-hand side to get. And that's it. That's our derivative using what they call logarithmic differentiation. All right, so hopefully that was a helpful video. Please reach out if you have any questions or want some more example problems, or if you have what if scenarios. I'd be glad to help you out, and I will see you hopefully sometime soon.